So welcome you all to my next video lecturing on expression for Fermi energy in terms of energy gap of an intrinsic semiconductor. So expression for Fermi energy in terms of energy gap of an intrinsic semiconductor. In my previous lecture we come across the what do you mean by semiconductor and what are the different types of semiconductor. So we have usually intrinsic semiconductor and extrinsic semiconductor, and in our whole chapter in our VTO syllabus we are mainly concentrating on intrinsic semiconductor, not on the extrinsic semiconductor. And also we come across the significance of the Fermi energy in an intrinsic semiconductor and as well as the extrinsic semiconductor. So after that we come across the expression for the number of electrons and number of holes. So let's recall the important definitions. The Fermi energy. So what do you mean by Fermi energy? It is the maximum energy. It is the maximum energy attained by an electron at 0 degree Kelvin. So it is the maximum energy attained by the electrons at the 0 degree Kelvin. Then that particular energy is called the Fermi energy. And what do you mean by EG? That is band gap. It is nothing but the difference between the energy levels between the conduction band and the valence band. It's the gap between the conduction band and the valence band is called the EG, that is band gap. So now we are going to derive an expression for Fermi energy in terms of EG. So initially we know that for any intrinsic semiconductor, the number of electrons, it is represented by Ne, is always equal to the number of holes. So the number of electrons in the conduction band is always equal to number of holes in the valence band. Let us concentrate on this particular topic first. So let us assume initially we have the valence band and the conduction band. Let us assume in valence band we have electrons. So we have electrons. In that electron, initially this electrons is in valence band. When we supply some amount of energy to this, when we supply through any of the means, through voltage or the temperature, what happen? This electrons starts moving to the conduction band, leaving an empty space, like this. So whatever the electron which is there, it goes to the excited state, leaving behind the empty space in the valence band, like this. The electron move like this, okay, leaving behind the an empty space. This empty space is nothing but holes. These holes usually exactly resembles the shape of an electron, exactly resembles the size and shape of the electron, but its charge is positive, not the negative. And even it has the capacity to conduct, or it has a capacity to move in around the space of that particular material. Okay, even not only the electron will move, even the holes will move. Okay, so hence even the holes also contribute to the conductivity. Okay, so while the number of electrons goes to the conduction band must be exactly equal to the number of holes created. So hence in an intrinsic semiconductor we consider that Ne is equal to Nh. And also we know that number of electron is equal to 4 root 2 by h cube, pi m star ekt to the power of 3 by 2 into exponential ef minus eg by kt. Okay, it's an exponential, the whole exponential term. Okay, and the number of holes is equal to 4 root 2 by h cube, pi m star h kt to the power of 3 by 2 exponential minus EF by KT. So let's use a small f only, doesn't matter. Okay, EF by KT. Okay, so where let us name this H is a Planck's constant by this is M. So here the M star represent the effective mass of the electron, not the real mass. It's an effective mass. There is a slight difference between the effective mass and the actual mass. So okay, K is the Boltzmann constant, T is the temperature, and EF is the Fermi energy, EG is the gap, energy gap, K is the Boltzmann constant, and T is the temperature again. And exactly the same here also, MH is the effective mass of the whole. Okay, so here even I say that the mass is almost same, electron mass and holes mass is same, but not the effective mass. Effective mass is quite different from each other, so hence we taken the effective mass. Okay, so now we come to know that Ne is 4 root 2 by h cube pi m star kt to the power of 3 by 2 af minus eg by kt, and Nh is equal to 4 root 2 by h cube pi m star h kt to the power of 3 by 2 exponential e minus ef by kt. So we know that Ne is equal to Nh, so we can write the equation like this: 4 root 2 by h cube pi m star e kt to the power of 3 by 2 exponential ef minus eg by kt is equal to 4 root 2 by h cube pi m star h kt to the power of 3 by 2 exponential minus ef by kt. Okay, so this is the term. Now let us cancel the common term, 4 root 2 by h cube, 4 root 2 by h cube, and next pi will cancel, kt will cancel, pi will cancel, kt will cancel. Only the left out with m star e, m star h to the power of 3 by 2, and here exponential ef minus eg by kt, here exponential ef by kt. So let's write that m e star 3 by 2 exponential ef minus eg by kt. Here it is m star h to the power of 3 by 2 exponential minus ef by kt. Okay, now what we do is, let us shift this exponential minus ef by kt to the LHS part. So then what happen is exponential, and let us cross multiply this me star to this side, RHS side. Okay, so ef minus eg, what happens if it comes to the LHS? It becomes plus ef, so totally by kt, and here that is m star h by me star to the power of 3 by 2. Okay, now what happened here? Ef, here ef, it becomes 2ef, so exponential 2ef minus eg by kt, here that is m star h by me star by 3 by 2. Now taking ln on, both side, because we need to cancel this exponential term, we need to take ln on both side. Okay, so let's continue here. So what happened to that equation? If you take a ln, what happened? 2ef minus eg by kt is equal to ln of m star h by me star 3 by 2. Okay, or we can come like this, 2EF is equal to take Eg to the RHS Eg plus KT ln M star H M E star 3 by 2 or EF is equal to Eg by 2 plus KT by 2 ln M star H by Me star to the power of 3 by 2. Since you are finding the expression for Fermi energy, this is the the final expression for Fermi energy. But if you exactly need to calculate the Fermi energy at T is equal to 0 degree Kelvin, so T is equal to 0, then EF becomes, if T is becomes everything, this term goes to be 0, this whole term goes to be 0. So hence EF is equal to Eg by 2. So this is the expression for Fermi energy at 0 degree Kelvin. So this is the final expression, and if you consider T is equal to 0, that is EF is nothing but Eg by 2. What is the meaning of that? So EF is always the exactly equal to the exactly resides at the half path between the energy gap. That means consider this is the conduction band and this is valence band. Eg by 2 means Fermi energy is always in between the conduction band and the valence band. So it is in between. So this is the meaning of this expression. So thank you. So have a great day.